or clarifying questions. Yeah, with that, Raaz, yeah, please take us away.
Thank you, Dominic. And thank you, Caroline and Ben, for organizing this wonderful workshop. I'm excited to present some ongoing work with Susan and Devrat about counterfactual inference in sequential experimental design. I'm relatively new to the field, so please pardon me if I miss something, but hopefully this will be a clear talk. And this will be a theoretical talk. And as Ben likes to call it, learning from theoretical interventions. Yeah, so sequential decision-making problems, they are arising in more and more domains, ranging from online education and online advertisements, where you want to enhance the teaching strategies or like ad placements, so in order to make the learning better or increase revenue. A particular application that motivates this talk is mobile health, which has become more and more common in the last few years, where you try to use mobile applications to notify users and encourage them to engage in healthy behavior. So you can imagine a mobile health application being some sort of physical activity recommendation app, which once in a while sends you a message to go take a walk or go out for a run. And the way they measure activities through some variable, they measure the step counts and stuff like that. So let me give a simplified but representative setup of this kind of a trial. We'll be in the Neyman-Rubin potential outcome framework. So YITA, there are like 3 scripts, but hopefully it will be clear throughout the talk. Potential outcome of user I at time t under treatment A. So those are the 3 different indices. And the way these trials are set up, so this is like you're trying to design an effective app. So you're running a trial beforehand to see whether the app works well or not, to optimize the app. And so for a capital T time periods, at each time, you go through all the users, capital N users, and you randomly send them a notification or not using some sort of policy. So policy here will be an n-dimensional vector of numbers between 0 and 1. And pi ti would denote the probability of sending user I at time t a notification given the history till time t minus 1. And once you send the notification or not, these are some preset times in the day, you observe some outcomes. So every user has a few times decided in the day. And at those times, you send them a notification or not. And then at the next 30 minutes, for example, you measure their step count. So that would be this outcome. And you have some noise in there because maybe the sensor is not perfect. And once you have this data for end users, you update your policy based on the data so far. And you keep doing this trial for capital T time periods. Okay. So the simplified view of this world is you have observed data for all users till time t minus 1. That determines the policy at time t. You have some unobserved potential outcomes and noise variables. So a policy pi t decides which treatments are assigned to which users at time t, and unobserved variables and the policy together decide what outcomes are observed at time t. And then this data put together decides your policy at the next time. You don't have to update the policy every day, but like every once in a while you do update it. So this is the design. And the policy here is adaptive so that you can personalize to different users so as to make the application effective. And in practice, sometimes you start pooling data during the study. So note how I write here all end users. That is being done to reduce the noise so that you can learn the policy quickly. Otherwise, if the users get frustrated, they might delete the app and they might just unenroll themselves from the trial. So there are 2 things here. The policy is known to you, it's adaptive, and it's being designed using all the data that you have observed across users. And some questions after the trial is over, general questions of interest would be, what was the treatment effect? Or like, what was the effectiveness of sending a notification? Was there heterogeneity across users? What was the treatment effect at time t? All these kind of generic questions can be asked. So our goal in this talk would be counterfactual inference. By that, I mean estimation of missing potential outcomes, which is a hard task in general because of heterogeneity across users and time. And you can imagine that if we can estimate all the missing potential outcomes, we can perhaps do generic after study analysis. But that part will not be the focus of the talk. Here, we'll assume that this is our goal, to estimate all the missing data. And heterogeneity makes it hard. Also, the fact that you have adaptivity and pooling of users during the trial itself to design the policy makes it even more challenging. Okay? And I will illustrate what I mean by this. So the next few slides, the outline will be like this. We'll look at the settings considered in prior work. there's a rich prior work with these adaptive policies. I'll try to differentiate how this setup is slightly different. And then we'll talk about our contributions, namely, we'll give a non-parametric strategy and then prove some sort of consistency and central limit theorem results under certain assumptions. So that will be the rest of the talk. So our setting is as follows. Just to recap again, we have n users time t till time capital T, and the data determines the policy. You observe observations at time t, then you use that information and the past information to decide your policy. So this might remind you of something like the dynamic treatment regime in longitudinal studies. Note that the way these boxes have changed is now we have one user. So these dynamic treatment regime problems, they focus on adaptive policies for a single fixed user over time. So this is like you're tracking an individual, his medical history, and based on their history and how they have responded to the treatments, you're adapting the treatments in an online manner. And you have these kind of experiments independent across users. So unlike our setup, where we have n users, the trial is being run simultaneously on them. Here, the trial is being run independently and separately for each user. In the recent literature on bandits, the setup is like this. It's like IID users over time. So it's like an ad setting. You have your performance, your policy till time t minus 1. That informs your, the data observed till t minus 1 informs your policy at time t. And then you have a new user, you use that information to update your policy. So here the users are changing over time. So you have adaptive policies, but it's not about the same users over multiple time instants. And then in causal panel data, you have multiple users simultaneously for multiple times, but generally the treatment is assigned only once, and there is no real discussion of policy in the literature. And often it's unobserved. So it's more like the unconfoundedness assumption and that kind of a setting. So it's again different than what we are trying to deal in this talk. So you might ask, okay, so what do you do? So we reduce in this setting counterfactual inference to a sequential matrix completion problem, meaning that I'll assume that we have finitely many treatments, and let's fix a treatment, for example, 1. Now we have n by t matrix of potential outcomes that we're interested in, and we only observe some of them based on which user was assigned action 1 at time t. In particular, the observation model now can be written as ZIT is Y star IT. Here Y star IT is the outcome corresponding to treatment that you fixed, plus noise if the action was 1, and unknown if the action was 0. And the actions here are being assigned using a Bernoulli flips using the policy at time t. Okay. And this policy is adaptive, as I said, using the data, past data. So now once you've reduced to this setting, the new goal is estimating the missing entries Y star IT. And we'll, as I said, we'll do it separately for each treatment. So going forward, we only have one treatment at a time. That's what I'll talk about. So the rest of the talk will be having reduced to sequential matrix completion. How do you estimate it? And when will this estimate be any good? Under what conditions can we show anything? For this, in general, a hard problem. So to estimate the missing data, we use a variant of nearest neighbors. So this is a matrix of n by t. Y-axis is the users. T-axis is the time. Blue boxes denotes the observed data. The gray, well, here it looks like white. White denotes the missing data. And suppose we are interested in estimating that particular entry YIT star, ith row, tth column. So to estimate that, the first step in nearest neighbors is look at the users that are available at that time, meaning that their outcome was observed at time t. Now restrict only to those users, and then compare the rows of any available user with the user I. Look at the time instance where both of them have a simultaneous observation. So these are 4 time instances in this particular example. Compute the square error distance between these 2 rows, limited to those indices. That is the distance rho t ij. So at time t, between user I and user j, when you are trying to estimate YIT star. So that's, the estimate is now very simple. It's average the outcome of available users whose distance rho tij is less than eta. Eta is some suitably chosen constant. So it's a very simple estimate. Find available users at time t, then look at their distance from user I. If it is less than eta, just average over all the available users. If you don't have any, if this set is empty, then you can choose a default value of 0 or mean over the entire set of observations. So eta, in our theoretical bounds, will track the dependence on eta. In practice, one can use some sort of cross-validation on the observed entries themselves. So there is a practical way of tuning eta, but for now, we can assume that eta is given to us and we'll track it in our theoretical results. So note a very special property of this estimate. It's completely model and policy agnostic. Like I'm not using propensity weights, I'm not using anything. So you don't need to know the pi t's to construct this estimator. And I'm not making any parametric assumptions on the model also. So it's very agnostic, and you might wonder, will it even work? Like, isn't it too general for it to work? And the talk, this second part of the talk is no, it is general, but it still works if you have some sort of a latent factor model assumptions and suitable conditions. Yes.
Temporal carryover effects.
Sorry, what?
The outcome at each time point for each unit, did they only depend on the treatment at that time point?
So why? Yes. So when I'm fixing YIT star, I'm assuming that unit I at time t has a unique outcome associated with action, that particular treatment. Yes. So there is no spillover in the future. That is correct. And it will become more clear when I present the next slide. Thank you. So what is the latent factor model that we assume? Let me go on this slide slightly slowly. So YIT star is the quantity of interest. And you can assume that, or you can think of it as the outcome of user I at time t for treatment 1. And we model it as a function of UI and VT, unknown function. And these UI and VT are latent factors. So we don't need to know any of them. UI represents the latent factor for user I, and VT represents the latent factor for time t, and F is unknown potentially nonlinear function. So this is a partial answer to your question. For different treatments, we'll assume a different F, UI, VT, and you can repeat the entire machinery to get an estimate. So that's how it's done separately for each treatment. But there is some sort of stationarity, but at the same time, non-stationarity that will become clear now. So let's visualize what this means. So y-axis is the end user latent factors. X-axis is the time latent factors. So at time 1, this model is saying that the outcome of unit 1 at time 1 is a function of its latent user factor U1 and V1. And yn1 star is a function of UN and V1. So you can see that V1 induces correlations across this whole column, although each user has a different way of taking a different snapshot of V1 because of that potential nonlinear function. And then across time, the user 1's outcomes are given as a function of U1 V1 at time 1, U1 V2 at time 2, and U1 VT at time capital T. So you can see that this kind of structure means the outcomes are correlated. So if I fix a time, they're correlated because the latent factor at time is fixed. If I fix a user, they're correlated across time because the user latent factor is fixed. So it's a special kind of correlation. Nonetheless, it is still a good model in the sense that even if these factors are IID, the outcomes are not IID because of this structure. Okay, so this is, now you might ask, why is this structure interesting other than correlation? Well, in these kind of trials, often you use Gaussian processes to model the outcomes. And Gaussian process is a special case of this particular latent factor model. So if yi star, so the outcomes of a particular user across time are a draw from a Gaussian process with kernel k, then ui denotes a Gaussian vector and vt denote the eigenfunctions. So vector corresponding to eigenfunctions of k. And this f is actually a bilinear function. The size of these vectors depends on the rank of the kernel. And also this setup subsumes a subclass of exchangeable data. Like, so if your matrix has exchangeable rows and columns, a subclass of that data is covered under latent factor model. So it's fairly general. And as I said, F doesn't have to be linear per se for our guarantees. So now I have told you that reduce the problem to matrix completion, then use nearest neighbors. And I've introduced the latent factor model. Now the point is, like, what can you do? What can you say with this kind of a structure? So let me first start with the bilinear case. Then I'll go to the nonlinear case. So in the bilinear case, meaning that if the outcomes are given as f of u comma v is an inner product between u and v, then for any pair it, so any user I at time t, remember the run of the experiment is capital T. So small t is some index in between. If it has enough nearest neighbors, that satisfy two conditions. First condition is that the latent time factors are diverse enough, meaning that if I take the latent factors, make their covariance matrix, it is positive definite with an eigenvalue smaller greater than lambda, and the sum indices are the common observed time points. So remember, we were constructing the distances. We are looking at when both units had commonly observed data point. Look at the latent factors on those time points and construct their covariance. That should have a minimum eigenvalue. So this is talking about that your latent factors are diverse enough. And the second assumption is if your noise is non-adversarial. So we had epsilons in our noise outcome model. So if our noise is not adversarial, because you have these adaptive sampling mechanisms, it can be adversarial. So if it behaves roughly like IID or mixing process, despite the adaptivity, then for suitable scaling of threshold eta and mild conditions on the policy. So in this case, actually policy can be arbitrary. It doesn't even have to be sequential. For a given unit, conditioned on its latent factor ui, we have a consistency result that our estimate goes to yit star for any t, not just the last t. It's like I'm going back in time to impute everything. So we have a consistency result as the number of units and the time goes to infinity. Yes.
This diverse latent time factors condition here,
yeah.
Is the matrix on the left-hand side a random one? And if so, then is this like, does this have to hold with probability 1, or what's the,
Great question. Yeah. So this is, we are trying to give, you should think of this as a deterministic assumption. So if you want to make distributional assumptions, then the statement here will depend on when this condition holds. So if this holds with high probability, this will hold with high probability. If as t goes to infinity, this holds with probability 1, then this will hold with probability 1. So it's like if and then kind of a condition. Okay. So here we are not making any distributional assumptions. We are just giving you the two objects that have to behave in a nice way.
But this is a random matrix.
This is, yes. So if you condition on everything, it's deterministic. If you're not, then yes, it is a random quantity. So you can think of this as going to the eigenvalue of the population level covariance, and that if population level covariance is well behaved, then this will be well behaved if the samples are enough. Okay. Thank you. Yes, sir.
Do you have uniform convergence over I?
No, this is for fixed I, and you can do So this is, if this holds for all t, then this will hold for all t. When will this hold for all t? That's the so you need conditions to make it a uniform probabilistic convergence. But if you have this for all t, then yes, it will be uniform. But here we are assuming that the user is fixed. So and we are proving convergence one by one. Yes.
What's the rate for the threshold constant?
Yeah. So for that, I will have to use my additional slide. We can do that during questions.
Is there any condition on the user latent factor?
Not in this slide now. Let me tell you why this will work in the next slide. So you'll see why it works is if the latent factors are diverse enough and the noise is non-adversarial, what ends up happening is that if the distance is less than eta, you have this ui minus uj times a matrix times ui minus uj sitting there. So it indirectly implies that ui minus uj have to be less than root eta by lambda, where lambda is that minimum eigenvalue. And once you have that the user latent factors are close, then the outcomes are close because we have bilinearity. And we can also handle approximate bilinearity for the same reason. So you can now see that if this lambda is 0, this bound is vacuous. And why do we need many users? Because we have noisy outcomes. So you need to average across the users to kill the noise. And yeah, so that's the rough intuition what is going on, why this bound will work. Yes.
Why are you calling this sequential matrix completion?
So this part handles sequential as a subset. It's more general than that. The next part is only about sequential. So I'll explain it in the next slide. Okay.
Oh, if I assume that, I think I might be missing something here. If I assume that f of u v is bilinear like this, does that imply that my matrix of y's is exactly rank 1? Or
No, no.
why is it not rank 1 is what I'm wondering.
Because you have ui's and vt's. So it's a matrix of u times v. Each of them will depend on the rank of the latent factor. So it's a rank R matrix if that is the dimension of your latent factors. It's not rank 1. All right, so coming to the sequential part and slightly stronger guarantee. So if f is not linear, now we assume it's a general nonlinear function as long as it's Lipschitz. And suppose we have these additional distributional conditions, and these are needed to provide a stronger guarantee. So previous result was just a consistency result. Here we'll be showing a central limit theorem. So we are also characterizing the fluctuations. So if the unit latent factors are IID, the time latent factors are IID, the noise doesn't have to be IID, but it's independent with mean 0 and variance sigma square. And your pi t is sequential in the sense that pi t depends only on the history till t minus 1. So this is the sequential part. And the treatments are assigned conditionally independent given the history. Then we can show that under regularity conditions, which I will elaborate, for any given user with its latent user factor ui, at last time t and the number of nearest neighbors nit, you have the right central limit theorem that the estimate minus the true thing root nit goes to normal 0 sigma square as the n and t go to infinity. Now they have to go together at a suitable rate. That will become clear later. So this is where sequential part comes in, because if you have an experiment of size n by t, we can only tell you guarantee at time t. So you can think of, you run the experiment till time t, you construct confidence intervals, make a decision and continue. So that's the sequential part. Yes.
But none of this is about deciding the policy to force these conditions, right? This is just completely based on like if you had
Yes.
a set of policies.
So that is correct. We are not designing policies. That's a great question. We are just saying that if your policy comes from in a most sequential experiment, it satisfies these properties, then these conditions hold, like this results hold. Yes.
But it could be potentially like it's not obvious how to design such policies.
Well, people are actually already running trial with such policies when they use like bandits data or multiplicative weights based on past data. So they update some sort of treatment of whether I should treat user I with treatment 1 with higher probability or not based on past data. So they are already doing it. So I would say this is fairly general, is already being done. What we are trying to say is, despite these kind of conditions, we are still able to do some sort of counterfactual inference under a latent factor model and these assumptions.
Sorry, Raaz, just one quick comment. So if you take questions from the audience now, can you just repeat them for the people who are online, because they might not hear it if it's not with the microphone?
Okay.
Yeah.
All right. So the question was, are we trying to tell how to design these policies? The answer is no. And the question was, is it clear how to design such policies? And the answer is yes, because it's already being done in practice using all kind of RL algorithms to run these trials. So in those settings, pi t actually satisfies these assumptions. This one in particular, this is debatable. That's like a modeling assumption. Yes, Ben.
The number of neighbors is implicit depending on threshold.
It depends on threshold, yes.
And implicitly assuming that goes into.
That's right. Yeah. So let's go to the next slide to see what this means. Here, everything is going to infinity. It's not clear who is going where. So let's see on the next slide. So to understand who is going where, we need to write a non-asymptotic bound. And we prove this in the paper too. So now I'm talking about an expected squared error bound on y hat it, capital T, minus y star it, given the user unit factor I. Expectation is over all the other randomness. You can potentially condition on VT if you want to, but we don't here. And then we have 3 terms on the bound. One is, this first term is the bias due to the eta. The second term is concentration of neighbor distance. I'll explain all these terms in a bit. And the third term is, because you are averaging over many users to estimate the outcome, the noise variance goes down. So that's the variance term. So these are the 3 terms. First 2 terms behave like the bias term actually. So what is P min T here? It's the minimum sampling probability of any entry till time t. So that is P min T. What is phi I? That's the phi I sitting here. That's the probability of sampling a good neighbor a priori. So before you ran the trial, we have the n users. what is the probability that you had one good user in that, for user I, you had one good user to begin with. That's this probability. And then this mysterious and slightly complicated term gamma IT, that captures the effect of your sequence of adaptive policies pi t in a stability sense. It's hard to parse it, but let me try. It is saying that look at the joint probabilities of I and j being treated at time t prime, condition on history at t, and subtract it with the same thing, condition on history t minus 1. So the only difference between the two terms is what you're conditioning on. And the difference is just one column. So this bound is meaningful only when gamma IT upon p mean square root t doesn't like diverge, it goes to 0. In other words, we want this gamma IT to grow slowly than the denominator. Or we want to say that the policy is adaptive in a stable manner. It's not adapting too quickly. 5 minutes. Okay, great. I'm almost on track. So the policy is not adapting too quickly. That's this meaning of gamma IT being small. And so now we have this squared error bound. To establish central limit theorem, we'll multiply the whole thing by the NIT, the number of nearest neighbors. And we'll only care about the bias should go to 0. So, before that, sorry. Maybe I'll come to this later. Yeah, so for the central limit theorem to hold, what I will do is I will multiply effectively. I'm multiplying this by NIT. So this thing gets multiplied by NIT, this thing gets multiplied by NIT. You can ignore this one for a moment. So this should go to 0 after multiplying by the number of nearest neighbor. That means the eta has to go to 0 fast enough. And if you multiply here, then you have NIT in the numerator and root t in the denominator, meaning that the number of nearest neighbors at time, they should be capital T, doesn't go faster than p square mean root t. So I can explain in the discussion afterwards, like why this kind of a condition arises here. But in a nutshell, we can make sure that this happens by capping the number of nearest neighbors for theoretical analysis. Like you can always cap to get a bound on how quickly p min t can go to 0 and things like that. So it's possible to send this to 0 at the right scaling of eta, p min, t, and by capping the number of nearest neighbors. So that's the bias term goes to 0. This is the variance term. So once you multiply by NIT, actually, this is the NIT term sitting there. So you have that sigma square. And so for central limit theorem to work, basically you need the denominator to go to infinity, and that will go to infinity if phi i's and p min t are like the right, like they scale correctly. That's it. So that's the whole talk. We were talking about sequential experiments where trials are run for capital time T. You have n users, and you pool across all the users' information to update your policies. And the question is, can we do counterfactual inference? I presented a simple nearest neighbor estimate, and then I showed that, or at least I told you, believe me, that under latent factor model, if you have bilinearity under suitable conditions, you have consistency result for any user and any arbitrary time. And if you have Lipschitz nonlinear F, then you have a central limit theorem for the last time point, and scaling by the number of nearest neighbors. You might have many questions, and want to put a disclaimer that this is just a starting point. As I said, I'm relatively new to this topic. It's very exciting. We have no context or features or covariates in this setup. That's one thing to do, how to incorporate that information. I said we are interested in counterfactual inference, and I said that we are interested in estimating all missing outcomes. But so once we estimate it, what do we do with it? What's the effect of that? That's another question. I'm assuming IID, and I'm not putting any structure on how the latent time factors are evolving over time, or how the user is evolving over time, or how the user is being impacted by treatment, as the question was from the audience. That is not being used. And I have separated counterfactual inference for each treatment to a separate matrix completion problem. So I'm not leveraging information across treatments. That is another. So because this is, in my head, this was like our first attempt to find when can we do it, and now try to unpack its further consequences. And preprint I submitted on archive today, so hopefully it will be online later today. Thank you.
All right, thank you very much for the nice talk. So I think it's good if we hold further questions for the panel discussion later and now have our break. So we're going to continue in half an hour with a talk by Jamie.